Hello everyone. We are today's webinar is on federated learning. Specifically, we'll discuss about the platform that Piotr has developed, that is Sunday FM. Yeah. As you all know, my name is Kawan Laksh. I'm from Warsaw Management University, and my second person who is going to present this webinar is Piotr Nistelia. He's from Department of Mathematics and Information Science from Warsaw University of Technology. It is one of the most prestigious universities in Warsaw. He has just completed his master's degree in informatics, and he is the actual developer of the platform that we are going to discuss. Now, the agenda of the webinar has already been shared with you, but just to sum up, we'll try to have an introduction of what Federation Learning is. We'll see the alternative platforms that enable Federation Learning. Then we'll see our platform, that is the Sunday FL platform, its architecture, implementation, and execution. This will be handled by Piotr. And at the end, we'll take the questions in the question answer sessions. And we'll try to answer them to the best of the ability. Yeah. Now, introduction to Federation Learning. Federated Learning, I'm really sorry. As we all know, in the old school assumptions of old school assumption, they are different restriction assumptions, such as number one, all data belongs to a single owner, and second, that all data is processed with a single computer. Now, the latter should be understood as follows. While it is possible that computing takes place within a network of workstations loosely connected using a PVM or a Condor middleware, all nodes have a single owner and should be treated jointly as a part of virtual computer. Now, keeping this in mind, let us reflect on changes that took place within the last few years and are still ongoing. Obviously, this list is not exhaustive. The first one is smartphones contain multiple, typically more than 10 sensors. Each of them can generate a data stream. While billions of smartphones are in use and this number is still growing, here on one hand, users may want to control data generated by their devices, that is their private data. On other hand, they may want to use this data for their advantage, that is, by deriving from it actionable knowledge. Here, note that users have data, they lack the capabilities required for processing it. Moreover, local data covers a limited fragment of knowledge and does not generalize. For instance, single person mobility patterns will not help improve smart city services, such as the one that has been launched in India by Prime Minister Modi. Uh, the status of the current project is unknown, but for this, mobility patterns of a majority of citizens are needed. The second one is, with technological advancements, the size and prices of sensors continue decreasing, while the number of aspects that can be measured is growing. This enables heterogeneous sensors to be easily placed at any location. Moreover, such sensors or cluster of sensors can belong to multiple stakeholders even if they measure the same parameter. Hence, delivery of user-centered applications require use of data belonging to different owners that may not be willing or they are not able to share it. The third one is proliferation of wireless networks, including deployments of 5G networks. That is our next point. They allow efficient implementation of sensor networks. This in turn makes it easy to establish communication channels between sensors, actuators, edge devices, computing nodes, gateways, cloud services, etc. 5G supports progress in research development and deployment of Internet of Things and their ecosystems. To deliver services to the users, such ecosystems are needed and they need to be broadly understood. Next is machine learning. Since popular machine learning approaches are based on large scale neural networks. And sixth one is hardware dedicated to neural network based machine learning. It has been developed already and it includes extra small devices that can be placed almost anywhere and may belong to different owners. Example of such devices are Intel Movidius, Nvidia Jetson Nano, but the number of such devices is large indeed. A lot of them can be found if you just Google it. Yeah, the last one is data is generated locally and it cannot be transferred to the cloud for processing, or the person do not want to transfer it to the cloud for processing. On one hand, data elements may be too large and too many, such as images that are generated behind a narrow bandwidth network, or they cannot be released, such as confidential or personal information such as your medical data, your legal records, etc. Now, what does this mean? This means that the vision of a single owner of data used to train the model to realize individual goal is not the only one. Thus, it should be obvious why federated learning has been proposed. Now, as you can see, there are different nodes, they have different data, and they do not have any model, or how will we they get the model? So what do we do here? We can see that there is a server, a network of nodes that share models rather than trading data with the server. Now this is the actual concept of federated learning. How does it takes place? Let us see that here we have a server and four different nodes. The server has an untrained model. It sends a copy of that model to each node. Now, these nodes also have this untrained model. Now, they also have data, and on this data, each node trains their model. Now, once they have trained this model, they will send this back to the server. Now, the server combines these models by taking an average. There are various different algorithms for this, but the fit average is the most common one. Now, the server has a model that captures the patterns in the training data of all the nodes, but at no point did the nodes share their training data. What they shared was their models. Now, uh, there are certain issues that we might also face during federated learning, such as it consumes a lot of power, there are drop connections, or there might be stragglers. So a platform has to develop accordingly, which handles all these different scenarios and is able to give out a very high accuracy. Now, another concern that may arise is data is secure, since none of the nodes have exchanged data, but the models they can be viewed by others and hence is unsecure. So this is also a field of interest. Alternative platforms. What are different alternative platforms that provide federated learning currently? There are very big players here such as Google or Nvidia, but the thing is these platforms, although they provide pretty decent tools for us to use, these are proprietary softwares. They force us to use their own platforms, and in the sense they limit our capability. As a community, we should strive towards more open source platforms. And yeah, let us discuss a few of them. Now, uh, let us start with TensorFlow Federated. The current version is 0.18.0, the last I checked. It is an open source platform for decentralized machine learning and other computations. It uses its own framework to facilitate federated learning. The FL API and the Federated Core FC API are the two layers that it supports. The FL API enables developers to apply federated learning and evaluation to TensorFlow models already in use. The FC API, that is the Federated Core API, is the FL cornerstone. It is a collection of low-level interfaces for implementing federated learning. It supports Mac and Linux platforms only. This does not support Windows. So this is a big limitation. The second one is PySyft. It is a Python library. The current version is, I believe, 0.3.0 for deep learning. It supports federated learning, differential privacy, and multi-party computation (MPC) in PyTorch. It supports Keras and TensorFlow as well. It runs on macOS, Linux, and Windows platforms. So this is slightly better. The third one is Fate. Now, the version for this is, I believe, 1.6.0. It is an open source project initiated by VBank. It implements multiple secure computation protocols to enable collaboration while supporting data protection regulation compliances. Available machine learning models include neural networks, GBDTs, and logistic regression. It runs on Linux and Mac OS, so this does not support Windows. Moreover, it provides MPC and harmonic encryption. Flow allows users to define their pipeline of the federated learning process. It may include data preprocessing, federated training, federated evaluation, model management, and model publishing. Now, finally, we have Flava. So this is actually a quite decent platform. It is, currently under development. It is designed to handle large number of clients, 10,000 or even more, and is actually platform independent. It supports Keras, TensorFlow, MXNet, and PyTorch. It allows running federated learning on Android, NVIDIA Jetson, macOS, and the Raspberry Pi. Now, as per its creators, it follows the following core principles: customizability. It allows individual configuration depending upon the needs. Extensibility for creation of modern state-of-the-art architectures. And it also allows for elements to be expanded and overwritten. So this is actually a promising platform. Now, Sunday FL. So moving on, as I earlier mentioned that the alternatives that we just discussed, a large amount of them are actually proprietary. So to move into a more open space, Piotr developed Sunday FL. Now, Sunday FL is actually based on Akka, which manages the federated learning, and then Akka calls Python, and in Python we actually implement it. So let us now welcome Piotr, who will present the federated learning part of the webinar.
Okay, hi, do you hear me well?
Yeah, Piotr, you're audible. Just let me end my screen share and then you can. Just a minute.
Okay.
Okay, now you're free to share your screen.
Okay, do you see the screen and the presentation?
Yes, Piotr, it's visible. Thank you.
Okay, so I will start to talk about SunDFL, its architecture and implementation details. Oh. So let's start from the assumptions. The conducted analysis of the literature led us to the following assumptions. So the first one is that the platform should be scalable. The second is that it should be runnable on various environments. It should also be easy to make changes so that the different ways of learning can be tested. It also should be possible to run the platform on the different machines. So now I will talk more about architecture details. Based on the approach described in Google article, we proposed our way to build the architecture of the federated learning system. It is based on the actor programming model. The design of the system architecture is driven by the necessity to manage a large number of devices. Another aspect that we have to take into account is the necessity of enabling system configuration. So it means that the client program can be able to run different machine learning scenarios. It should be easy to set which algorithm will be used and with what parameters. Also, more complicated scenarios should be runnable easily. To allow this, we propose design where the client can download the proper module according to the machine learning task in which he would like to participate in. Another problem we have to consider is the fact that the device may perform machine learning task in a specific time slot. Sometimes the number of participants may be too small. For example, in case when the problem concerns on a business issue. If a few components would like to perform machine learning, then might be too small clients to enable machine learning in different time slots. So they have to communicate to decide a time slot in which everyone can participate. Currently, this is a functionality that is not implemented yet, but it will be implemented in the future. However, it must be taken into account when we designing the architecture. So the proposed architecture is composed of the following components. The major is the cooperation manager. It is responsible for determining the time slot details. Each personal agent sends a possible time slot in which it can participate in learning. Based on that, the cooperation manager determines the proper time slot. It is important that the diagram does not specify how exactly negotiation should look like, and it might be dependent on the some details aspects. And it just takes into account the necessity of that module. The second important component is the injector agent. It enables client program configuration. It manages a set of modules that are needed for machine learning. A client can download the module necessary for run a specific machine learning task. Another component is the coordinator. It is the main actor responsible for synchronization and managing rounds. There might be multiple coordinators, and each one is responsible for specific machine learning task. Within specific machine learning task, there is one coordinator for the entire training process. The coordinator spawns the master aggregator, which is the long-living actor that manages each round. Another component is regional aggregator, which is short-lived actor, which manages a single round. So it's living within only one round, and it is responsible for communication with personal agent. It also reports changes to the master aggregator. An additional component might be a verificator. This is optional actor and will be available in the future. It's not implemented yet. And its main feature is to verify the whole process. So let's consider the example that client may have bad intentions and intentionally would like to harm the model. In that scenario, verificator checks if an update may improve the model. If not, the changes are rejected and will be not taken into account when the model will be aggregated. So one of the last components is personal actor, which represents each device. It participates in negotiations, and the negotiations will be implemented in the future, as I told before. It is also responsible for handling modules needed for learning. For example, it is responsible for downloading the proper module from using communicating with injector agent. Oh, and it also asks to join in machine learning round. And the last component I would like to discuss is computation helper. It is planned to facilitate the realization of complex workflows. A case for its use is, for instance, when a device is not capable to handle computation itself, for example, IoT devices. So let me start by describing how the process looks like. So I mean how one round of training is performed. Let's start with key facts. The first is that each device knows about the server, and it has its address. The server doesn't know about the device until it sends the request that it wants to participate in learning. At the beginning, the device notifies the server of willingness to participate in training. So after the needed components are found, device asks to participate in run. The server collects information about such devices for a specified period of time. Then the server arranges the training details with the devices. This includes determining when the training is to take place and on what principles. So it could be, for example, the training model and its various parameters that are to be selected. For example, neural network. So once this information is established, the learning phase begins. Each device needs to download module needed to run training on their local data, and more details about this process will be talked. I will talk about it on the next slide. I would like to also talk that there are two ways to carry out training: synchronous and asynchronous. The synchronous approach is that the runs go one way. Asynchronous, on the other hand, so that several runs are executed at the same time. Both approaches have been used with success, but recent trends are moving towards synchronous learning due to the Google article. Therefore, in this work, the architecture will be such as to enable synchronous learning. So, as I told before, the important feature of the platform is handling modules. One of the platform's advantages is the ability, which helps user to train models in a variety of ways. It should be similar to how the model would be conditioned, which is a unique structure. The user must then load the required module, which enables training, before the process can begin. It's important to emphasize that the user can only download the module if it's necessary. And there are two types of modules, one running on the server side and the other type, which is running on the client side, and it's depicted in this picture. So the client module part is responsible for the informing the server of its data in such a way as not to share it. And the second feature is that module is starting a TCP connection to allow connection to the server. And the server module is responsible for connecting with all client modules, which will be participating in the round, starting the learning process, which consists of the following steps: sending the model to clients, conducting client-side learning, downloading the model, and connecting the model. So now I'd like to talk more about this algorithm. The main idea is shown on the right side of the screen. So in the beginning, personal actor of the client checks if has a needed module for the task that he wants to perform. If he already has the module, then he can join learning, and this is the end of that scenario. If not, personal agent asks the injector for the modules list. Modules list are stored in a server application as a JSON file, and here is presented a simple sample format with two modules. All modules are stored in one directory. They can be accessed using their file name. So this is property file name here. The modules are Python files, but they can be any files that are executable from the terminal and meet the requirements. So after that, the personal actor receives the modules list in a JSON format I talked before. Then he chooses the module best suited for himself and downloads it. Download module means that the client sends a request to the server, and after that the module is sent back to the personal agent, and personal agent saves the module in a proper directory on his side. In this slide, I would like to describe how a module is structured and what needs to be done to add a new module. So, as I told before, the module is divided into two parts. One is running on the server side and another is running on the client side. To add a new module, add the server and the Python and the client parts, which will work together to train model. And the main idea is that the client should accept the following parameters. So that's all I presented, and about architecture. And now maybe let's move on to the how to execute the platform. So do you see the IntelliJ window?
Yes, Piotr, it's visible. Can you please also give a brief description about the various folders that are there in the project, which are the important ones, something about that?
Okay, so the most important folders are the client and the server, and as the name follows, the client has a client part of the application and the server part of the application. Here are stored the main actors. They correspond to the components I've presented on the picture. And the most important part is here when the module is executed. And the server part, the components also correspond to the components that I talk about on the architecture diagram. And here is the main component, which is responsible for manage learning. So do you have any more questions about the project structure and anything else?
Uh, Thanks, Piotr. Can you please show us the execution and explain about it? Thank you.
Yes. So first we should start the server part of the application. So it should be started with this command. So the server has started. We have information that components were created, and the task ID is MNIST, so it's corresponding to digit recognition problem. And now we have to run client. Oh, another thing that I would like to show you is the configuration file, which have the most important information about how to perform learning. Epochs mean how many epochs are performed on the client side, and my minimum number of devices is the minimal number of devices that should take part in one round. So here I've set this parameter to 2. So because of that, I have to run 2 clients. So the server is already running, and I have to run client. Let's start one client. So it's called Alice. And another called Bob. We can see that the client got a response that he can join the round. Same as the other client. And then now we have to the module has started running, so the client informs about their data set and waits the server to connect. And now the server should start the learning. So here you can see that the number of devices connected in this round is 2. So the learning phase should start immediately. So and now learning begins. Oh, this is weird that the accuracy is less than at the beginning, but I don't know the reason. But nevertheless, the server performed 5 epochs and saved a model in that file. And if you would like to perform another round, the model will be loaded from this file and sent to the client. So this is all I prepared for today. And do you have any questions about the platform?
Yes, Piotr, thank you so much. Can you please stop your screen sharing? We have 2 more slides that I have to cover, and then we'll take the question answer session.
Okay.
Yeah, thank you. Okay, guys, we have now covered our platform, Sunday FL. You are now acquainted with how the platform was developed, what technologies were actually used to develop it, how do we execute it, what are different folders that are important, and in case you want to, read some more information and gather some more insights on this platform, as well as the research carried out. Uh, we also have a publication. The publication is called Sunday FL, Developing Open Source Platform for Federated Learning. As you can see, Piotr is the lead author, and the rest of the authors are as follows. I'm also one of them. It is going to be published in 2021 Emerging Trends in Industry 4.0 ATI 4.0 conference in the IEEE Explore. The preprint is already available on ResearchGate. So you can just download the file from there. The full text is available. For those of you who want to start playing with this platform as soon as we can, please join us. We will be happy to have you. We already have a large team of around 20 people who is parallelly working on this. So here is the GitHub repository. You can clone from it. There are 3 branches: dev, QA, and master. Just start from dev. Yeah. Thank you so much. Now we'll have the QA session. Just a moment. Yeah, let's start.
Hi, am I audible?
Yeah, Antalin, you're audible.
Yeah, Piotr. So I was going to run this on a VM because I don't really have a Linux system. I use Windows. So is there any system requirements that I should be aware of?
Piotr, can you
Memory
please share system requirements, the basic requirements that a person should have to run the current project as it is?
So the main system requirement is that that it was tested only using Linux, and only Noninesh tried to run the platform on Windows, but I don't know about the results. I know that there was some problem, and it might be problematic, but it should be easily runnable on Linux. There need to be the components that are need to be installed are Akka, TensorFlow, and PySyft in a specific versions. And I can send you the proper versions by the email.
Yeah, thank you, Piotr. Can you mention which operating system you're using?
I'm using Ubuntu.
Okay, thank you. Guys, I also had a conversation with other people who are currently working on the platform. You can use off the shelf any Linux platform for this. The Sunday FL platform also runs on Windows, but due to a vendor dependency with TensorFlow, there is some issues, but the platform is actually running. So the learning part, there are some issues, but the federated learning management is actually running. So yeah. Next question, please.
Oh, I can only add
Hello.
that I prepared the Docker, so it might be runnable via Docker. So please ask your question now.
Am I audible? Hello.
Yes, you're audible. Please continue.
So this federated learning is totally dependent on the multiple local nodes or devices. So my question is, like for testing this Sunday FL platform, what should be the minimum number of local devices or nodes we should use for getting the most efficient result? Like here we have used only 2, which Piotr demonstrated us. So what should be the minimum number of devices or nodes that we should use to get the best results?
Yeah, Piotr, in your master's thesis and during the experiment that you run on IST, where you compared the various, approaches for this, how many instances did you run, and what was the best result?
So I had to add that running multiple instances is really processor consuming. That might be problematic to run more than I think 10 clients within one machine. And when I perform testing, I used the maximum number of devices I used was 10, and when I perform tests with more number of clients, I was using the local simulation, so I was using the platform without communication within TCP, and of course it is natural that the more device and client participates in the training, the better results are achieved, and the best results I achieved was with 20 clients, but I haven't tested the more number of clients.
Okay, so Piotr, that we can assume that on a normal machine that we usually have on our end, a normal laptop that we usually use, let us say like an i5 processor or an i3 processor with around 4 GB of RAM, you suggest like the maximum number to be used is around 10, but with more processing power, we can increase this number, right?
Yes, this number could be increased if the parameter of the machine will be better, because I have only 12 gigabytes of RAM, and this is the main limitation.
Okay, thank you, Piotr. I believe this answers your question, right? Do you have anything else to ask? Maybe another question, guys?
No,
Last
Lakshman,
one
that's all
from my
from my
end.
side.
Yeah, can I go ahead?
Yeah, please continue.
Yeah. So last one from my end. If is there a rejection criteria for a client if he has a very little data which leads to some unreliably trained model, and so we end up rejecting that model? Is there some criteria for that, or do we accept everything that comes in?
Piotr, I believe we addressed this in our project, right? The various selection and rejection criteria, how master nodes selects whether it wants a particular client in the learning session or not. Can you please elaborate something on this?
So do you mean the case when the client has not enough data to participate in training?
Yeah, it
Yeah.
can be like not enough data, or it can be not enough processing power, or any of the criteria that is not met, that is actually required for the learning inclusement.
So if the client has not enough computation power, with take that possibility into account, and prepared a component that is called verificator, which is responsible for helping device with computation, and it is trusted component that that client can trust it, and it might be deployed within one organization behind the gateway. And in that case, client sends all data and model to that computation helper, and it performs the training itself. And if client has not enough data, there are a few techniques to deal with it, and the most common is data augmentation, which means that the client manipulates with his data. For example, if we consider a digit recognition problem, the client can make more examples by shifting images in some ways. So using that technique, there might be more examples, and it should shift in better accuracy.
Yeah, Thank you, Piotr. So from your answer, I understand that the question that this person asked, it is being handled by the verificator part of the architecture, right? And as you
Yes,
mentioned
yes,
earlier, if I'm correct, that verificator is currently under development. Am I correct?
yes. Under development, it will be developed soon. It's only taken into account in architecture diagram, and architecture is prepared for that component, but it's not implemented.
Okay, so in the next release, guys, we'll have this added into the platform as well. But if you want, you can implement it on your end and maybe share it with us so we can compare our approaches. Yeah, thank you, guys. Any other questions for the session?
No, that's it from my end.
Okay. So thank you so much, guys, for joining our session. Thank you for being patient. Uh, as I said, that this is a developing platform and it is open source. So we'll actually be very grateful if you could actively join the development and make some valuable contributions. Now, as I said, you can reach out to Piotr or me via our emails. You can see from the screen the Piotr and my emails. Uh, and you can message us for any queries that you have. All right, guys. Piotr, can you give a small introduction about yourself? I believe I mistakenly pronounced your name incorrectly. Maybe a few lines about your education, your current occupation, and what motivated you towards federated learning.
So yesterday I ended my master studies and I get my master diploma. And as Nalinash told before, I was studying at Warsaw University of Technology, and I decided uh, to develop a platform for federated learning because it's a relatively new field of study, and there are uh, no no enough flexible tools to perform federated learning process.
Okay, thank you so much, Piotr. We're really grateful for joining us, being the original author of the paper as well as the original creator of the platform. Thank you very much, guys, for joining us. We are now going to wrap this session. In case you have any further questions, please feel free to write us on the emails. Thank you so much, guys. Have a wonderful night.
Thank you.
Thank you. Thank you.
Thank you.